All right, so yesterday we talked about the SN1 reaction versus the SN2 reaction. We said in the SN1 reaction, we go through a carbocation intermediate. So the main thing we have to look at is whether or not we're forming a stable carbocation. So if we have a resonance stabilized carbocation or tertiary, that's really good. If we have a primary or methyl carbocation, that's bad, right? So we can use that to determine the probability of an SN1 reaction. SN2 reactions are a little bit different. We said instead of looking at carbocations, we're just simply looking at how crowded the carbon is with the leaving group. So let's kind of combine this together, just because a few people asked me about this in my office. We'll say tertiary, secondary, primary. Actually, I'm going to take out these, and methyl. These are all the carbon with the leaving group attached. All right, so as we go this way, which one's more likely, SN1 or SN2? Okay, so SN1 is more likely. Conversely, if we go the opposite direction, that means that SN2 is more likely. We can make some quick assumptions, right? So if we've got a primary or a methyl group, that's really likely going to be SN2. If we have a tertiary carbon, or in this case, one thing I left out is resonance. If we have either of these, then that's likely going to be SN1, right? So then the main question is, well, what about this one? What if we have a secondary carbon with the leaving group on there? Can do either. We're going to talk about tips and tricks for determining which one's more likely if you have a secondary carbon with a leaving group coming off of it. A lot of it doesn't depend on the carbon itself. Instead, what we have to look at is things like solvent or our nucleophile. All right, so yesterday we started talking about the nucleophile. So in an SN1 reaction, we said the nucleophile just doesn't matter because it's not involved in the rate limiting step. So SN1 reactions, you don't need a very good nucleophile in order for it to occur. You still need add nucleophile, it just doesn't need to be really strong. And then in SN2 down here, we took this situation where we had iodide as our nucleophile in reaction A, bromide as our nucleophile in reaction B. We said that bromide's smaller and less stable, therefore it would be the better nucleophile if we're ignoring solvent. All right, I've got another one though. So let's do a second example regarding nucleophiles. Shoot, let's do reaction A over here, and then we'll do reaction B below it. So we'll use the same electrophile with the leaving group for both of these reactions. Keep that variable the same. But in the top reaction, I'm going to use this nucleophile. And in the bottom reaction, I'll do this one. And again, we're going to do an SN2 process with with each of these. All right, not SN1, SN2. So what will the first step be in an SN2 reaction? Well, does the leaving group fall off first in SN1 or SN2? That occurs in SN1. These are both SN2. So in SN2, we're going to show that backside attack, kick off our leaving group in both of these situations. All right, thought experiment. Which of these reactions will be more favorable? Check with your neighbor and try to argue. Do you think A is more favorable or do you think B is more favorable? All right, let's kind of get back to our cardio rules that we talked about yesterday. Which of these is more stable as a nucleophile, or do you think they're about the same stability? According to the cardio rules, what do you think? They're about the same, right? So in terms of stability, we've got an oxygen with a negative charge, no resonance in either case, no dipole induction, nothing like that. So these seem very comparable in terms of their stability, right? So we can't differentiate them that way. How else could we differentiate them? So I think weight is a good idea. What's another term we could use that might be better than weight? Not mass.
We're in the same ballpark.
Sterics. What does sterics mean? How crowded it is. All right, do you think it's better if our nucleophile is sterically bulky and crowded? Or is it better if our nucleophile is less bulky, less crowded? Less bulky. Okay, so we could go up here and we could say that this is less bulky. Therefore, it is easier to attack the carbon. All right, so in this case, I think we've got a really good claim that reaction A is faster, or I should say is more favorable, because the nucleophile is less bulky. So there's two main things we have to look at with nucleophiles, right? Down here we said stability isn't the full story. We also have to take into account how sterically bulky something is as well. So typically a good nucleophile is two things. A good nucleophile is something that is unstable. So let's make a note. Another way of saying this is it has a negative charge. Without much stabilization. Meaning it doesn't have resonance, no dipole induction, making it happy. It's something with a negative charge that isn't super duper happy. So it's unstable, and what was the other thing that's super important? Sterically unbulky, so not bulky. All right, so these are the two key features of a good nucleophile. We have to pay attention to both of them when we're looking at this. Does that make sense? All right. So now let's go to our next page. Actually, I'm going to skip this for right now, and instead we're going to jump to solvent, and then we'll go back to that page. How about that? All right, so what we've been ignoring so far is the solvent that the reaction takes place in. What's the role of a solvent? It normally doesn't participate in the reaction. It's just the thing that your solutes dissolve in, right? So a solvent is there to dissolve things. However, sometimes it can facilitate a reaction. So let's make a note that reactions have transition states that can be stabilized by solvent. What happens during a transition state? Yeah, bonds are half broken and half made. So if we can stabilize the making and breaking of bonds, what does that do to our activation energy? Could lower the activation energy, right? So let's take a look at the SN1 transition state. All right, in an SN1 reaction, the transition state involves what bonds being made and or broken? What's the rate limiting step for an SN1 reaction? Leaving group falling off. Okay. So during this step, we could have our leaving group kind of falling off. The leaving group, when it falls off, is partial negative. The carbon is becoming positive, so it would be partial positive. This would be our transition state. Let's do an SN2 transition state. During an SN2 transition state, we said yesterday what happens is the nucleophile will do a backside attack of a carbon. In this case, it'll be a methyl carbon, and then our leaving group will fall off the opposite side. What shape was this? Trigonal bipyramidal, exactly. So we can go ahead and say this is the transition state. If we look at both of these transition states, they have similarities to them. Do you see how we've got polarization occurring, meaning we've got portions of the molecule that are really electron rich or electron poor? So I would say both transition states are polarized. We've got electron rich, electron poor regions in both of them. All right, what sort of solvent do you think could help stabilize a polar transition state? A polar solvent or a non-polar solvent? Polar solvent. Okay, so let's make a note. And lower the activation energy. So what I mean by that is, let's imagine our activation energy for our rate limiting step. I'm just going to pick one like this. If we think about this, the black line would be equal to a non-polar solvent. Let's do a red line for a polar solvent. The red one would make this transition state jump a little bit smaller for each of these, right? So it would help stabilize that transition state by stabilizing that polarization of the molecule. Does that make sense? Okay, so a polar solvent is good for both SN1 and SN2. So polar solvents work best for SN1 and SN2. All right, so that's good. We typically want something that's quite polar. So let's go ahead and look at our common solvents in an organic chemistry sheet. I know I gave this to you quite a while ago, but let's identify the best solvents that we could use for SN1 and SN2. Should I use polar Protic solvents for SN1 or SN2? Are they polar? Yeah, I'd say this works. So that's okay. What about polar aprotic? Yep. What does polar aprotic mean versus polar Protic? What's the main difference between these classes? The ability to hydrogen bond, right? So polar Protic on the top, those can all hydrogen bond. Can polar aprotic? No. All right, what about the non-polar ones? Would these be any good for SN1 or SN2? No. So we would avoid using these solvents, but maybe we could choose from polar Protic or polar aprotic. So let's try to investigate this further. We're going to dive into polar Protic versus aprotic. All right, so let's do polar Protic on the left. How did we define polar Protic again? What was unique about them? They can hydrogen bond. All right, so we'll say can H bond. For polar aprotic solvents, they're a little bit different. They cannot H bond. All right, so let's think about our nucleophile. So I'm just going to draw a generic nucleophile with a negative charge right here. We're just going to assume that it's kind of in this cloud of electron density, right? Then over here, kind of same thing. We'll consider our nucleophile here. Let's pick a polar protic solvent. So can anybody give me an example of a polar protic solvent, something that can H bond? Water. Sure, why not? All right, so water. If you think about this, what's nice with this is we can have a bunch of water molecules kind of floating around. Why are the hydrogens all going to orient towards the nucleophile? Yeah, because they have a partial positive charge. In addition, we've got something else besides that partial positive that can really stabilize this nucleophile. What's going on here? Hydrogen bonding, right? So in this case, a polar protic solvent will actually form a solvation sphere around your nucleophile. All right, so let's make a note. So protic solvents will H bond to our nucleophile. All right, my question for you is, let's focus on polar protic right now. Will this affect an SN1 reaction very much? What do you think? Does the nucleophile matter very much in an SN1 reaction? No. Okay, so let's make a note. This won't impact SN1 because the nucleophile doesn't participate in the rate limiting step. All right, let's consider an SN2 reaction, right? Because right now we just focused on SN1. What about an SN2 reaction? Is this a good or a bad thing for an SN2 reaction to have hydrogen bonds around your nucleophile? Why do you think bad? So I'm hearing some people say you have to have energy to rip apart those hydrogen bonds so that the nucleophile can attack the carbon, right? So that's one way of thinking about it. The other thing to think about it is we said that H bonding in this case is stabilizing the nucleophile. We just finished saying we want an unstable nucleophile, right? Unstable nucleophiles are going to be more reactive. So let's make a note here. This is bad for SN2 because we want an unstable nucleophile that isn't wrapped up in solvent. All right, so let's kind of look back at this. So a polar protic solvent we said is bad for SN2, doesn't really make a difference in SN1. So polar protic solvents, what do you think they're best for? SN1, right? In this case, polar protic solvents are great for SN1 because they're really, really polar. H bonding solvents are incredibly polar, but it doesn't really matter about the nucleophile because it's not involved in the rate limiting step. All right, so let's make a note here that this is best for SN1. All right, make sense? Let's go on to our aprotic solvents. Aprotic solvents we said cannot H bond. So I'll just pick one of our aprotic solvents. So let's go up in our sheet. So we've got acetone over here. So I'm just going to pick on acetone for right now. So acetone's a nice aprotic solvent. It's one we use in lab a lot for cleaning. All right, so my question for you is we've got acetone molecules. I'm going to draw two of them. You don't need to copy these down. My question is, does acetone orient itself so that its legs are facing the nucleophile or the oxygen? Why the legs? Yeah, if we think about this, it's got a net dipole, so we prefer to orient so that the partial positive side is closer to the negative charge on our nucleophile. So it kind of forms this staggered orientation around it. All right, so in this case, there is a weaker interaction between solvent and the nucleophile because no H bonding can occur. So there still is a dipole ion interaction, but dipole ion interactions are considerably weaker than H bond ion interactions, right? So if you remember back from Gen Chem, this is a much, much weaker electrostatic force. All right, so in this case, it's not wrapping up the nucleophile very much. So it weakly solvates the nucleophile. All right, in this case, do you think this is going to impact an SN1 reaction? No. So let's make a note. In fact, I'm just going to cheat and copy. See if this works. Maybe I'm going to embarrass myself. And put it over here and say, all right, this won't impact an SN1 for the exact same reason we just recommended, right? All right, so let's think about the SN2 reaction. Is it going to impact the SN2 reaction? If so, is it a little, a lot? What would we say?
Yes, but a little.
Yeah, so it will impact SN2. But not as bad. And the most important thing is it is still better than a nonpolar solvent. Why is it still better than a nonpolar solvent?
Wouldn't the polar molecule not even mix with the nonpolar solvent?
Yeah, so is it, first of all, is it going to be very easy to mix a negative charge in a nonpolar solvent? No, so A, it's going to be a crummy solvent. And then up here we said that polar solvents are really important for stabilizing the transition state. So we want a polar solvent, we just want the least bad of the polar solvents. Does that make sense? So down here we would say this is best for SN2. Why wouldn't we use a polar aprotic solvent for SN1? Does anybody have an argument for that?
Polar Protic is better.
Yeah, polar protic, we said, is better because it's more polar, right? Polar protic is a lot more polar than polar aprotic because it can H bond, right? So it's going to be best for SN1 because it will stabilize the transition state. All right, does that make sense? I know this is kind of a little conceptually challenging. All right, so let's consider SN1 again. What was the rate limiting step for an SN1 reaction again? Leaving group falling off? How can we facilitate this? With solvent. What do you think? Rate determining step. Sorry, that should be a RDS. Rate determining step. Good question. Feel free to stop me if my chicken scratch makes no sense. All right, how can we facilitate the leaving group falling off with solvent? Do we want a polar solvent or a non-polar solvent, first of all? Polar. So right now we're just focusing on SN1 only. So we said that polar solvents will stabilize the transition state, but between the polar solvents, what will stabilize the transition state more? We said H bonding is best. So getting back to our other point, H-bonding solvents are the most polar solvents we have at our disposal. It'll stabilize that transition state more, but there's also an additional feature going on. If we think about the leaving group falling off, is it good to have something H-bonding to that leaving group as it's falling off? Let's think about it. Let's draw this. Everyone's like, no, wait, no, he stopped. Yes, yes. Okay, so I'm going to draw a partial positive, partial negative. Let's draw a polar protic solvent. If we look at each of these, the cool thing that's going on here is a polar protic solvent will actually hydrogen bond to your leaving group as it's starting to fall off. This is helpful, right? Because we ultimately want that leaving group to fall off because that's the rate limiting step in this reaction. So not only is it beneficial to just have a polar solvent, but the H bonding of that leaving group as it's falling off also helps too. Yep.
Would the oxygen on the water start to bond a little bit with the positive charge in the carbon?
That's a good question. So the question was, does the oxygen on the water start to associate with the carbocation? Kind of. It depends on a couple of things. One is whether or not the carbon's super crowded, meaning can very many water molecules get in there? That's one thing. However, the other thing is actually getting into my next point. What do you think would happen if that oxygen were to start to associate with that carbon with the positive charge? What sort of bond do you think we could make? Let's think about this. We could make a new covalent bond between oxygen and carbon. In that case, the oxygen in water could act as a nucleophile, all right? So it's a little bit weird to think about. So let's make some notes here. And in fact, I'm going to include that in our note. First one is polar aprotic is best for SN2. Polar protic is best for SN1. And then in SN1, your solvent is often your nucleophile. So in the above reaction, just like Eric was saying, what if the oxygen starts to associate with one of these carbons over here, right? Because this can also be a good interaction. Well, if that occurs, then we've essentially created a nucleophilic attack whereby that oxygen forms a new covalent bond with that carbon. So it's something we have to watch out for in SN2 reactions. Is water a very good nucleophile? What do you think? It's got a lone pair, but does it have a negative charge that's unstable? No. So water is generally considered a weak nucleophile, but in an SN1 reaction, does the nucleophile matter anyways? No. So in this case, it's good enough for an SN1. Yeah, these are really good questions. All right. So the next one is going to make you all angry at me. So deep down the rabbit hole. This is where things start to get confusing. So let's compare some nucleophiles. Got hydroxide, got the sulfur analog, and we've got the selenium analog. If we look at these, they're all in the same column of the periodic table, right? We're just going down that column. All right, which one's most basic? Why is OH most basic? So this is most basic. Another thing we could say is as we go down, this is most stable. Right? Why is the selenium compound with the negative charge most stable? It's got the largest electron cloud, right? Biggest atomic radius makes it happy with that negative charge. Therefore, oxygen with a pretty small electron cloud isn't as happy. It wants to steal a proton back. So that's one way we can look at this. Okay, so let's, on the other side, consider solvents. All right, so on the left-hand side, we'll do solvent arrows. Let's consider an aprotic solvent. So over here, sorry, I'm just going to erase this. Which one's going to be the best nucleophile in an aprotic solvent? And remember, an aprotic solvent loosely wraps around your nucleophile, but not a whole heck of a lot. Which one's going to be most nucleophilic and aprotic? So let's think about this. I would say a nucleophile is best if it's less stable, right? So in this case, I would say OH minus being less stable is still going to be the best nucleophile in an aprotic solvent. Does that make sense?
So does the basicity play a part in this?
So in this case, the basicity is correlated to the nucleophilicity, right? All right, let's consider, though, our other solvent. What if we're in a polar protic solvent that can H bond? Do you think the same trend is going to be true? Let's think about this. Which one's going to H bond more tightly with the H bonding solvent? The oxygen or the selenium?
Oxygen.
The oxygen, why?
More electronegative.
It's more electronegative. What else?
Less stable.
It's one of the chemicals that can actually hydrogen bond. I think that's an excellent description, right? So if we can think about this one, this can H bond. With polar protic solvent. So then when we think about it, if we're H bonding with the polar protic solvent, is that a good thing or a bad thing for the nucleophilicity? Do we want our nucleophiles to H bond to the solvent? No. So that's a bad thing. So in fact, we observe an opposite trend on the other side, where this would be protic, and this would be more nucleophilic. So nucleophilicity can actually change depending on what solvent you're in. If you're in an aprotic solvent, we prefer to have really unstable small nucleophiles, right? If you're in a polar protic solvent, you want a nucleophile that's not very good at H bonding, meaning you want a large atomic radius. It's kind of weird to think about. The tricky thing is, normally we don't use polar protic solvents for SN2 because that kind of gums things up anyway, but we might run into situations where we encounter this. So I feel like I have to show it to you. All right, so let's do another one. What about nucleophiles in the same row? We just looked at nucleophiles in the same column, but let's take a look at some in the same row. So I'll do NH2, we'll do OH, we'll do F minus. All of these are in the same row, nitrogen, oxygen, and fluorine. All right, which one's most stable? Ooh, let's think about this again. Go through the cardio rules. If we're in the same row, do you look at size or something else? Electronegativity. So which one's more electronegative? Fluorine. So this is more stable due to electronegativity. All right. Do we want our nucleophiles to be really stable or really unstable? Unstable. All right. The good thing with these is solvent doesn't really change things here. Does that make sense? Because let's think about a hydrogen bonding solvent. Which one's going to hydrogen bond most tightly? Let's think about it. Which one's going to hydrogen bond super duper tightly? Yeah, the fluoride, right? Because fluoride's super electronegative, it's super tiny, so solvent's going to quickly wrap up this tiny electron cloud. Versus nitrogen with a negative charge, it's less electronegative, a lot bigger, it's going to be harder to completely wrap it up with solvent. All right? So we said fluoride, if it's hydrogen bonding, is going to be a crummy nucleophile, which again matches this. So again, it matches both stability and solvent coordination. So solvent doesn't really change much here. This is a lot easier to understand. All right? Let's do a couple more. What about weak/neutral nucleophiles? So let's do two of these. We'll do same column. And then over here we'll do same row. So same column. So we'll do ethanol down here. And then the sulfur analog right below. So these are in the same column, right? So oxygen versus sulfur is really the only difference here. Which one's going to be a better nucleophile? The top one or the bottom one? And why? This one's tricky. So when things are neutral and we're not really comparing negative charges, cardio rules can't really be applied, right? Because we're not stabilizing a negative charge. This one gets abstract. What do you think?
Is that supposed to be CH2, CH2?
Oh, sorry, this should be CH3. Thank you. That's why I keep you around. Keep me honest. What do you think? So you're saying let's think about the size of the atom, right? So sulfur is pretty big, oxygen's relatively small compared to sulfur. I think that's an important thing. Let's think about this. What can this do that the other one can't? Can hydrogen bond, all right? What is it going to H bond to? Solvent if it's polar protic, or it could just H bond to itself too, right? So it can H bond to itself. Oh. Is that a good thing or a bad thing? If it can H bond to itself, is it going to be a very good nucleophile? No, exactly. So as we go down this row, this gets more, or down the column, excuse me, this gets more nucleophilic. Another way of describing this is the polarizability of the lone pair on the sulfur versus oxygen. If we think about the lone pairs on the oxygen versus the sulfur, which lone pair is going to be held a heck of a lot more tightly? The oxygen, right? So those lone pairs are going to be held close to that oxygen atom. Why? Because it's smaller and more electronegative, right? The sulfur is going to have this giant electron cloud with electrons far away. Because those electrons are far away, they're going to be looking for something to attack, right? They're going to be held less tightly by the parent atom. All right, so that's a really useful one to think about. Let's think about same row. So in this one, I'll do NH3 versus water. Both of these are in the same row, nitrogen versus oxygen. They're both neutral. All right, so same idea. Which one's going to be a better nucleophile? So both of these can H bond, right? That kind of complicates things. Which one's going to hold on to its lone pair more tightly between nitrogen and oxygen?
Oxygen.
Oxygen's definitely going to hold on to its lone pairs more tightly. Is a good nucleophile one that holds on to its lone pair tightly or one that wants to donate a lone pair? wants to donate it. Okay, so again, we can say that this one gets more nucleophilic this way, because this lone pair is held less tightly due to electronegativity. Does that make sense? I know this is heavy-duty conceptual stuff. All right, so now let's go back to that handout that I gave you. Relative strengths of nucleophiles and talking about solvent and basicity. This kind of takes this super complicated topic and smashes it together into one common thing. So like we said, we can correlate the strength of nucleophiles to basicity, but they're really not the same thing all the time. It depends on the solvent. So down here, a nucleophile is described as something that has the lowest activation energy. So good nucleophiles has a low activation energy, right? That's the big thing with the nucleophiles. We got to get over that hump. All right, let's go to the next page though. With basicity, do we look at activation energy, or what are we looking at with basicity? With basicity, instead, what we're really looking at is delta G. The interesting thing as we go up is activation energy depends on the height of these transition states, right? We said that we can stabilize those transition states with solvents, or destabilize them with solvents for that matter. So this is really impacted by solvent. Because solvent changes the transition state energy. All right, what about basicity? Does solvent really change the transition state energy a whole lot for basicity, or does it not even get looked at with basicity? Not really looked at with basicity. Basicity, we don't look at transition state. We only look at delta G. The activation energy is completely ignored with basicity. All right, so as you go down here, there's a good summary of nucleophiles on this guy's website, Master Organic Chemistry. I find oftentimes I explain it and students are like, yeah, you explained it. It made sense in class. And then 10 minutes later, I had no idea what you were talking about. Sometimes hearing it explained a slightly different way can be helpful too, so you're welcome to check out this link as well, and then read through the handout as well. All right, so that's where we'll stop today. I'll give you a hint on the pod though before we leave. All right, problem of the day 21. Last year, I think like a third of my class didn't read the directions. There's an SN1 reaction being discussed here. What's the first step in an SN1 reaction? Leaving group falls off. All right. After the leaving group falls off, we get an intermediate, right? That intermediate is a carbocation. What could happen with a carbocation? Rearrangement. So that's my hint. Is watch out for rearrangements. Sound good? All right. Good luck studying this weekend. If anything comes up, feel free to email me and I'll try to help you out. I'll also be around tomorrow too if you want to set up any appointments.